Hello guys, so we are Senior Design Group 3 and today we're going to be showcasing our midterm demo. I'm Ryan Rodriguez.
I'm Abdullah Al-Garabali.
And I'm Tiffany Tani.
We will start with our photonics and optics section.
Here in our CAD model, I'm highlighting the imaging path through the center optical stack to where the skin sample would be at the bottom. The purple case with a handle is to hold the polarizing film. As I move this part into the main stack, you can see how the two parts surrounding the polarizing film hold it together. The handle attached will make the polarization manually adjustable for the user's preference when imaging. The gray components surrounding the stack now form the main enclosure. They keep the optical elements aligned and block stray light from reaching the camera lenses. On the base, there are small holes for the LEDs, and as I rotate the model, you can also see the aperture and optical filter wheel sandwiched between the lenses. This CAD drawing does not include the electrical hardware, LEDs, wiring, or PCBs, for example, but will be added onto this and completely enclosed in the main housing unit around this optical stack. Next, we'll show how we tested these optical components before 3D printing the enclosures based on our measured dimensions.
Okay, so as shown in the 3D printing section, this is our optical stack. I'm going to go through component by component and let you know the setup. So starting with the sample, we then have our infinity corrected lens system using two achromatic doublet lenses. The first being a 5mm lens with a 12.5mm focal length, and the second lens is encased right here, which has a 25mm focal length. And it's infinity corrected because the space in between the two lenses is equal to the sum of the two focal lengths. To go over some other components that we're going to have in here, in between this section is going to be our filter wheel with 3 filters that are going to iterate in order to allow us to take multiple images. We have a linear polarizer that we're going to have here that's going to rotate, allowing us to change the polarization of the light we want to capture. And then we also have in here, we have an iris right here to be able to change the depth of field for our images. And then lastly, we have up here our camera module, which is a Sony IMX219, which we use to do all the magic. And yeah, that's pretty much it. Raspberry Pi, and then I'm going to pass it off to Tatiana.
So here we created a set of layered silicone phantoms to use in place of live subjects for our preliminary testing. So this is one of them here. The phantoms shown here in the petri dishes, they all represent different skin tones that we controlled by adjusting the amounts of silicpig pigments and titanium dioxide mixed in to mimic the light scattering that occurs within human skin. Each phantom was cast in a 9.5 centimeter diameter petri dish and contains a thin pigmented epidermis layer between approximately 0.3 and 1.2 millimeters thick. So that would be, yeah, these are the two different layers. You can see a little bit more clearly. The thicker, more translucent dermis layer on the bottom, which is the pink that you can see, is between 2 and 6 millimeters thick. Some samples also include small embedded channels designed to simulate subsurface blood vessels. This is important for optical imaging, so we can test the different wavelengths when it comes to this. For each skin tone, we casted samples at 1, 2, and 4 millimeters thick to prepare for reflectance and transmitted some measurements using light-emitting diodes operating at 470, 530, 630, 850, and 940 nanometers. We first measured clear silicone samples to establish a baseline for absorption before adding pigments and scattering agents. The pigment and titanium dioxide levels were then fine-tuned until each phantom visually matched the appearance and optical depth expected for its intended skin tone. The collected images allowed us to observe differences in brightnesses, color, and contrast across different skin tones and wavelengths, as well as how deeper features became more visible under near IR illumination, near infrared. These phantoms now serve as a controlled test platform for the next phase of analysis, where we will calculate the scattering coefficient and absorption coefficient and the spatial resolution of the imaging system that we have here before moving on to testing with live subjects.
Now we'll be moving on to the hardware components.
This is the LED driver board. It is equipped with 6 N-channel MOSFETs, each capable of controlling up to 6 LEDs. In total, the system supports 36 LEDs, red, green, blue, white, 940, and 850 nanometer infrared wavelengths. The brightness of each LED is individually controlled using pulse width modulation, allowing smooth fading sequences as demonstrated here. This is the stepper motor driver board. It utilizes the ULN 2003 driver and 4 standard digital input-output pins for control. Due to the unique pin layout of this board and the absence of jumper cable, the motor board is activated using a separate generic Arduino for demonstration purposes. This allows precise rotational control without hardware modifications. The ATM328 microcontroller board serves as the central control unit. It generates pulse width modulation signals that regulate the LED brightness and, in standard operation, the motor outputs. By adjusting the duty cycles of these signals, the system achieves variable intensity for LEDs and precise motor control for actuators. The 12 volt is regulated by the buck converter, which outputs a stable 5 volts. This regulated voltage powers the ATM Mega 328, the LED driver board, and the motor board, ensuring reliable operation across all subsystems.
And moving on to software.
The Arduino software starts with the white LED on to capture a color balanced image. Afterwards, based on the hex value of the center pixel of the image, we will step through the red, green, blue, 850 nanometers, and 940 nanometers LEDs. All the colored LED channels are turned on, but each LED dims and rises based on data from the image captured. Now I will walk you through the image processing techniques involved. But first, let's capture an image. The Pi posts the original and annotated images to the Node Express API, which uploads the files to Cloudinary and saves the metadata in MongoDB. Here we can see the image being uploaded to our full stack website. Metadata is stored in JSON fields which contain information such as the hex code, image processing time, resolution, and detected regions. Express and Node use an in-memory multer to stream the buffer into the Cloudinary SDK. On success, we get a public ID and secure URL pointing to the MongoDB in Cloudinary.
The React client fetches the image and renders UI cards that have each image uploaded with its respective metadata and an image annotated with its potential abnormality detected.
On the image analysis side, we look for regions that stand out from their surroundings. We convert the image to a perceptual color space and for each pixel, measure how different it is from a locally smooth background. We use delta E as a color distance score. If that score is high, those pixels get grouped into a candidate region. We then clean the shapes and keep only solid, well-formed regions. If anything survives this analysis, it gets a red box. And if nothing meaningful is found, we draw a green border around the image to make it clear that there were no findings.
Now let's move on to system specifications. So here we have a log containing our metadata. We have different sections. The hex column refers to how long it took to determine the central hex code. The detect column contains both image processing and upload time. That varies with size and also network conditions. So you'll notice a few spikes in that chart. Those aren't errors. That happens when we intentionally switch to a more aggressive detection method to enhance abnormality sensitivity. Also, the total processing time per scan is also how long the Pi spends on the heavy lifting, such as loading the frame, computing color difference features against local backgrounds, doing region and blob detection, and also drawing annotations. But overall, the pattern shows the expected accuracy versus latency trade-off when we crank up that detection sensitivity.
So now I'm going to be going over the last two demoable specs. So the next one is our feature resolution and spatial resolution. So basically what I have done is taken a bunch of sample images and I'm using a quick Python GUI that will load an image from my computer that we have previously taken. See, this is an image we've previously taken, and then I can draw a box around the region of interest and analyze, and it gives me the amount of pixels that the region covers and the feature size, as well as the spatial resolution, which allows us to collect data and other things on our system. Next, we're going to be talking about the last specification, which is penetration depth. So basically, we've made a bunch of samples And what we're going to do is control the depth of each layer, having a dermis layer and an epidermis layer. That will allow us to know which wavelengths are able to penetrate through different layers, and us being able to know those wavelengths will allow us to calculate penetration depth. So that is the intended plan for this last demoable specification. Thank you.
And that concludes our midterm demo. Thank you for watching, and please stay tuned for our final demo.